Dear students, welcome to the second week of our offshore production engineering course. So in this week, let me give you the schedule again, as we already discussed for the last week video. So today we will mention about the historical background of the geology and the reservoir of oil and gas, which is very crucial for the offshore environment as well, like onshore environment. So we will give some details, some basic information, which will be the basement of our course for the next weeks, right? Okay, so I will start by giving some information regarding on the historical background of offshore in oil and gas industry. So the first offshore well producing oil was drilled in 1897, which is after 38 years of the famous Colonel Drake's well in Santa Barbara Channel and at Summerland. We all know this one. It was drilled, this well drilled from a 250 feet wooden pier extension. And the production of the steel piers started in the late of the 1920s, extending nearly 40 meters into the sea, actually, all right? So it was the first well that has been drilled in the end of the 19th century, and then it's extended by time, right? So the truly modern offshore industry began in the course in the Gulf of Mexico, all right? The first successful well was October 1937. It was nearly 14-15 feet of water length, and a bit over a mile from the Louisiana coast. All right, the well was heralded to modern industry. However, it was completed by Kerr McPhee in 1947. Right. So although this well was in shallow water, about 20 feet, it was drilled out of the sight of the land, and the rig was movable, and the major patterns of future offshore development were established. Right. So the world's largest offshore oil discovery in Saudi Arabia's Safania happened soon afterward in 1951, with the first production in 1957, 6 year of the construction part, and then it started to the first production, which was also relatively shallow well, right? So by time it started to go deeper and deeper, right? And by time also it started to be developed, the technology that started to be developed actually, right? So by the 1980s, the deep water meant about 18 feet of water actually. Okay, that's what I can say. So as the industry is matured, drilling occurred in progressively deeper waters. So, for example, by 2008, anything less than 1,500 feet was commonly considered shallow. So the definitions vary, but the 1,500 feet and above are now considered as deep water, and with the depths more than 7,000 feet, often called ultra deep water. Okay, today's technology. As water depth increased, there was a move away from the fixed platforms to cheaper and more mobile submersible and semi-submersible platforms, as well as also the drill ships as well, right? So the tallest fixed steel platform was the Royal Dutch Shell. It was in 1989, Bullwinkle in the Gulf of Mexico, actually, Manatee Field. The structure of that was nearly 1,386 feet tall, with 1,026 feet of water, and used nearly 44.5 tons of steel on 9,500 tons of peeling. Right, so lots of metals is used, so as you can see. And the first floating drilling vessel was commissioned for this in 1953, which was capable of drilling in water depths ranging from 400 to 3,000 feet at that time. And the first versatile deep water drill ship was the name of that was the Glomar Challenger of the Global Marine Co. It was from USA and commissioned in 1968, and having a water depth rating of 20,000 feet and a drilling depth of 2,500 feet with the facilities of satellite navigation and the dynamic positions DPV call. I will mention next week's. So dynamic positioning is also included to this well, right? This platform. Okay. So the discoveries of the Protho Bay in 1968 and the Cook Park in 1969, is established in the Alaska North Slope, which extended activities in the Arctic offshore, actually, for the continental shelves of the United States and Canada. So the period between 1973 through to the 1990s saw the discovery and the development of giant offshore fields in North Sea, Mexico, the Caspian, the Arctic Sea, and Brazil even, as well as the Atlantic near Canada. All right. So lots of operations started with the development of technology. All right. So this period also saw the first deepwater discoveries in the U.S. part of the Gulf of Mexico, which is very famous with the Deepwater Horizon, you remember, right? Later on. So since 1990, there have been some giant offshore discoveries also in the west of Africa, all right, Brazil and the U.S. the Gulf of Mexico that we can say in total. So the overall global success rate since 1985, what we can say, has been accepted as 30%, whereas in earlier years it was closer to 9%, all right. So it's 30%. So one of each three drilled well, you can find the oil and gas, right? That's what we can say. So the discoveries, the early major discoveries in the North Sea were Brand in about 460 feet of water, in the Ekofisk in about 250 feet of the water. So the depth was around 3,090 feet. Have been reached in the North Sea, Norwegian Sea projects as well. All right. So in Brazil's Campos Basin, water depths can reach nearly 10,000 feet, and in offshore west of Africa, nearly 5,500 feet. Potentially significant recent deepwater discovery of Chevron's 2006 with this number 2 of Jack number 2 well in the Gulf of Mexico. It was drilled not only for the 7,000 feet of water, but also more than 20,000 feet under the seafloor. So it was a very big project. It's a kind of milestone project, actually. That's what we can say, which has affected the offshore industry a lot, right? Okay. So let's talk a little bit about the genesis. Okay, the genesis, we say genesis of offshore. All right. Offshore is simply a particular region of sea or ocean, we can say. Right? So the oceans have been in existence for at least 3 billion years, more than half of the age of the Earth, that we can say. All right. So let's say 4.5 billion years of the age of the Earth, and 3 billion years of that, the existence of the oceans that we can find. All right. So yet the origin of the oceans is still in doubt. But the topographical features of the planet are changing the continuously that we know, albeit slowly relative to the human lifespan. So during the main ice age, the seas were 100 or 200 meters below their present level, owing to the presence of the large volumes of frozen water. All right, and the land masses were consequently larger in that time. And presently, the Earth is emerging from an ice age. So to understand the genesis, let us assume that the planet Earth possesses a geometric symmetry. Okay, possesses a geometric symmetry. So essentially, the Earth would then consist of three major regions: solid material of the variable but generally large density, right? So liquid or moderate density, and gases of low density as well. So these three are the main factors. So these regions will be held together by the gravitational attraction, and the substances stratified into a central core of very heavy metal surrounded by the successive smooth spherical shells of heavy rock, light rock, water, and finally the gas layers. Okay. So the Earth may thus be compared with a wet football. Okay, a wet football. The hydrosphere being a relatively thin film of water on the surface of a large solid sphere that we can think, all right? That we can think. Okay. So let's continue with the genesis of shore. So in reality, land masses protrude through the surface of the hydrosphere, so that water covers only about 71% of the total surface area. So furthermore, the ratio of the water to land in the southern hemisphere is considerably greater, 4 to 1, than in the northern hemisphere, 1.5 to 1, right? So the average depth of the ocean is close to 4 kilometers. So the sea is smaller body of the water, often surrounded by land or island chains and possess local distinguishing characteristics. Okay, so that's what we can say actually, right? So that's why actually what I can say essentially there is but one ocean and all the land masses are islands. Let's think about it. So for the convenience, however, the ocean is divided into 5 principal regions, each displaying important differences of the detail in their characteristics. Right? That's how we can explain the genesis of offshore actually historically. So, okay, I can describe some terms in this type. For example, one of them is the shore. All right, shore can be defined as a part of the land mass. All right, which is closest to the sea and which has been modified by the action of the sea. Right? Shore. So the beach. Beach, we can say it is the seaward limit of the shore and extends roughly from the highest to the lowest tide levels. Okay. So shore, as you can see here. All right. So you are in the continent part. All right. So I don't know how you can see here. You can see it clearly or not. You can see it clearly or not, I don't know, but as you can see here, so shore shelf is here, continental shelf, and the beach part is the upper part of this one, right? And there's a tidal movement of that, it's sometimes from high to low according to the the change of the movement of the moon. It shows an effect of that, right? So another one is the continental shelf. This is the gently sloping between 1 to 1 in 500 extension of the land seaward bordering continents, which is covered by shallow water, altogether amounting to some 24 million square kilometers or 5.5% of the Earth's surface. All right. So what we can say, the outer edge of the shelf is normally normally where the inclination of the seabed suddenly steepens, marking the start of the continental slope. All right, that's what we can say. So suddenly the slope starts here. So mainly this is the main generic continental shelf description that we can see. All right. So another one is the continental slope. So for the continental slope is this part, as you can see here, after the shelf. So it's a narrow strip of relatively sloping seabed which extends from the continental shelf. It is seldom more than 80 kilometers wide, often much less, while the water is over it generally exceeds 1,500 meters in depth, and sometimes it's over 5,000 meters. All right, that's what we can say. So this is the range of the slope. It's coming after the shelf and before the rise part. What is rise? Continental rise is seaward of the continental slope. There is generally another slight slope. Okay, second slope. It makes a kind of slope like this, and then this is the lower slope. Probably in most cases lower slope. It's half of that, maybe nearly half of that. Right. So seaward of the continental slope, there is generally another slight slope called the continental rise, just before the seabed plunges down to the great depths of the abyssal plain. Water depth range from 1,400 to 1,500 meters average. Okay. So after that, it starts a kind of another mapping, which is belong through to the seabed. So we have to be very careful when we are making our pipelines, or if you want to make any drilling near here. So we will discuss all of these in details in upcoming weeks. All right, in upcoming weeks. So we will clarify it. Another one that we call is the deep sea bottom abyssal plain. All right, that's what we already discussed. It's the most extensive area and depths of the 3 to 6 kilometer occur over 76% of the ocean basin. All right, so it consists of flatlands, although isolated mountain peaks, which occasionally rise high enough to become islands and reach with woolly trenches along the middle dot these plains. All right. So we will discuss all of these in future weeks in details. Okay. So let's talk a little bit about the geology, background of the geology and the reservoir cases that we are facing in the offshore environment. All right, offshore reservoirs as well. All right. So rocks, we already know that all rocks in Earth classified in three major groups. What are these? The igneous rock, metamorphic rocks, and the sedimentary rocks. All right. So the first rock generated in the earth by the solidification of the molten magma is known as the igneous rock, right? So these rocks are composed of the natural crystalline aggregates of minerals at high temperature. And these rocks are hard, massive, and large bodies and well abundant on the crust as well as within the deep crust. Okay, you can see some examples of that: basalt, pumice, obsidian, rhyolite, scoriodacite, granite, gabbro, diabase, diorite. All right, this type of examples that we can give for the igneous rock. Right, so this is the first type. And the second type of rocks, we say metamorphic rocks. All right, so the metamorphic rocks are generated by the solid phase transformation of the igneous and the sedimentary rocks by the effect of the high pressure and temperature. So pressure and temperature we call PT from now on. The change of the crustal zone are responsible for the change in the mineralogical composition of the igneous and sedimentary rock in a solid-solid system. To generate new metamorphic rocks, the metamorphic reconstitution involves solid-state reaction we call neocrystallization. All right. To form what? To form new stable minerals and change in grain boundaries. Recrystallization we call it. All right. So as demanded by the new PT environment, so when pre-existing rocks introduced to an environment, all right, there are different, which are different from that in which they were originally formed. They begin to respond to the new physical and chemical conditions through change in the mineralogy, structure, and texture as well. All right. So this change can take place as isochemically, which is without any change in the overall chemical composition, or metasomatically, we can say, by the gain or loss of chemical constituents. Right? So thereby changing the overall chemical composition. All right, that's what we can say regarding on the metamorphic rock. So they saw some chemical differentiation by time regarding on some change. All right, some parameters which is affecting them. That's what we can say to sum up. Okay, the third one is the sedimentary rocks. We are already familiar with that one because, as you know, most of the oil and gas can be found in the porous parts of these sedimentary rocks as well. So they are already known by the oil and gas industry as the secondary rocks, which are produced from the degradation of the pre-existing igneous and metamorphic rocks actually. So the primary processes involved in the formation of the sedimentary rocks are weathering, erosion, transportation, deposition, and compaction in the exact sequence actually. All right, that's what we can say. You can see some examples: breccia, caliche, chalk, chert, coal, conglomerate, diatomite, limestone, sandstone, shales, rock salt, gypsum are the main examples of these that we can say. So what we can say, the weathering of the pre-existing rocks involves both mechanical disintegration as well as the chemical decomposition. Okay, chemical decomposition. So in the process of the disintegration, the rocks are broken up due to the disruptor effects of forces in the air and water currents, large change in the diurnal range of the temperature, and the volume change in the freezing of water, for example, can be happening. So similarly, pre-existing rocks are decomposed by the solvent action of water, which consists of the dissolved gases acquired while falling through the Earth's atmosphere. Okay, so this is actually how they formed, how they in the Earth crust, how they formed the formation part of these sedimentary rocks actually, and the examples can be seen in the figure here. So I will talk about the sedimentation and the diagenesis. So sediments are settled in a relatively low areas like lakes, river beds, or below sea level. All right. So they remain there and they do not get eroded. So if space is created for the additional layers on top. Okay. As the sediments accumulate and they get buried, the temperature and the pressure increase, expelling water from the sediments because diagenesis. Right. So here the clay, we already know, the clay becomes shale, losing over 80% of the water in the process. And sand becomes sandstone, losing only 5 to 25% of its water, right? So in the sedimentary environment, different sedimentary environments result in different rock characteristics. Some rock characteristics allow rocks to become the reservoir rocks, okay, reservoir rocks. So they are both what? Porous and permeable. It's very important. So what we are looking for the reservoir, it has to be porous and it has to be permeable, right? So it's very crucial. Okay. So in the beginning of the sedimentary rock, what we said in this is a sediment in water. Okay. For example, a beach sand, like grains are separate, right? As this is buried deeper and deeper, and the pressure forces out of the water and creates the rock, right? So this is the sedimentary rock that we call porous and permeability. It has a certain amount of the porosity inside and the permeability as well, which enables to transmit from one pore to the other pore the fluid itself, all right? Gas, petroleum, or oil, gas, or water, all right? So this is very important. Okay. So there are some very sedimentary environments that I would like to talk in here. As you can see, lakes, deserts, river, delta, glacier, beach, continental slope, deep sea, continental shelf, organic reefs, glaciers are here. The tidal flat, kind of example for the tidal flat, can be seen in here. And the continental margin, it's the whole continental margin, can be seen here, and the deep sea is a part of that in here as well. So this is an attempt to give some idea of the various sedimentary environments. Okay, this is very crucial, figure. It gives a good idea regarding on the different type of sedimentary environments. Obviously, this is somewhat actually for shortened version. That's what I can say, but it's very crucial one. For example, let's talk about the continental. All right, so the alluvial environment encompasses the river channel itself, the border of the channel, okay, the border of the channel, and the flat valley floor on either side of the channel that's covered by the water, and when the river flows, all right, when the river flows. It gives a good explanation. A desert environment, for example, is arid, all right, desert environment is arid. And the sediments there is formed by the combination of the wind action and the work of rivers that flow mostly intermittently actually through to it, all right? So it's another formation. So another one is the shoreline, okay, the shoreline itself, all right? So in the shoreline environments are dominated by the dynamics of what? Waves, tides, and the currents of the rocky and sandy shores, okay? It's very important. And the marine part itself. So marine part is the continental shelf environments are located in the shallow waters of the continental shores, all right? And where the sedimentation is controlled by the relatively gentle currents in here, not like beach sides which are in open sea. Relatively gentle currents are dominated in here. So the continental margin environments are found in the deeper waters at the edge of the continents. So where the sediments is deposited by a special type of the deep water current, right? So the depositional environment often plays a vital role, a crucial role of crucial part of the evolution. Crucial part of the evaluation of a well and the field as well. This often defines the major lithology and points to the possibilities of minor minerals. For example, the shell of one of the delta in the slide can produce some conglomerate, but the deep water is showing shales, fine sediments, okay, much more, which has a very low permeability. So clues to the deposition come from a lot of measurements in and around the well. So core data is invaluable for the fossils, something that can be seen on the logs, all right? So the analysis of the deep matter curves was always one of the first steps to choosing the deposition environment. Later, the imaging tools have been made the process much easier with high resolution borehole images, for example. Okay. All right, let's move. So, depositional environments in general. So, the reservoir rock types are clastic or non-clastic, classified in two different sections. The depositional characteristics of the rocks affect reservoir properties like pore volume and the flow properties. So the type of the porosity, especially in carbonates, is determined by the depositional environment. So this is a crucial point that we have to record. All right. The type of the porosity, especially in carbonates, is determined by the depositional environment. So the depositional environment determines the geometry of the reservoir as well. Rivers, deltas, reefs, and some sort of them as well, etc. have specific external geometries and internal properties here. All right. For example, an example of changing properties with the deposition is water depth. A clastic rock, clastic rocks are deposited by, for example, a river into the sea. All right, from river into the sea. The first deposits are the coarser sediments as they fall out of the river first. Okay, the finer grains are taken further out into the deep ocean. So sediments deposited in the deep water will form poor quality reservoir rocks as the fine grains lead to poor permeability as well. It's a good example, okay, how it changed. So from the structure and how it happened historically and today's structure that you can see, you can also imagine what type of mapping you can do, all right? So it can give a kind of rough idea to you, right? Okay. I would like to mention about the hydrocarbon formation, the source rock, how it's formed, the creation and the accumulation of the hydrocarbons in it as well. So let's talk a little bit about that. First of all, we have to say that there is a temperature window for the formation of the hydrocarbons, okay? So this is between 140 Fahrenheit through to the 325 Fahrenheit, okay? This is the temperature window. And of course, with the depth, your temperature is increasing, right? So if the temperature is too low for the hydrocarbon formation, it's below 140 Fahrenheit. If it is exceeds the 140 Fahrenheit and up to nearly 240s, all right, 240s, 230s, so oil can be formed, and then from 230s to 325 Fahrenheit, gas is possible to be formed. I'm talking about source rock. Don't think about the gravity in here, all right? I'm talking about the source rock. And then the temperature is too high for the hydrocarbon formation if it's above 325 Fahrenheit. Okay, so if the temperature is too low, the organic material cannot transform to the hydrocarbon, stays as an organic material but cannot be transformed. If the temperature is too high, the organic material and hydrocarbons are destroyed. So what happens? Some more solid structures can be formed, like what? Like diamonds, for example. Okay, or coal. Okay, coal and diamonds we can say. Okay, the exposure by time, 100 million years maybe, all right, and the pressure and the temperature, high pressure and high temperature, the formation will be much more solid than oil and gas, all right? Okay, so let's go. So for the hydrocarbon accumulation, this is crucial to enable 5 different factors for the hydrocarbon accumulation. We can say, first of all, we can mention about the major source rock, migration pathway. So from this source rock, it has to be migrated through the reservoir rock, and then there must be a trap above this reservoir rock to make a kind of trap to the fluid, all right? to keep it in that place and prevent to move it through the upwards and through to the surface. All right. And then there is a seal is the fifth factor that we can talk. All right. Okay, these five factors is a crucial part that we have to deal with and understand well for both onshore and offshore environments, reservoirs that we are talking, right? Okay. So for the source rock, what we can say is the accumulation of the organic matter firstly happens, and then preservation of the organic matter in there, all right? And there's a thermal maturity that we already mentioned for the subsurface heat and the oil window, all right? And let's say for the source rock, nearly 65% of the all source rock that we faced with is shale. All right, 20% around is marl, 21% around 21% of them is carbonate, and 2% of that is coal. All right, this is a kind of statistical results that I would like to give to you. All right, so hydrocarbon migration after it's formed in the source rock, so there's a need to migrate. Okay, so because why? Because the source rock is impermeable. All right, very low permeability test. I am talking about the conventional way, by the way, not unconventional. Okay, if you are talking about the unconventional, it's possible to produce from the shales as well. But I am talking about the conventional way in here. Okay. So what I can say in here, it needs to be migrate to a porous and permeable location, which we identify as reservoir, right? So hydrocarbon migrates and take place in two different stages. One of them is the primary migration and the secondary migration. In the primary migration, from the source rock through the porous rock it happens. So this is a complex process and not fully understand actually, right? We could not understand it yet fully, but it's happening some way, and it's probably limited to limited with few hundred of meters, right? 100 meters, 500, 600, 1000, maybe up to 1000 maybe, all right? So for the secondary migration along the porous rock to the trap, okay? So from the source rock to porous rock and porous rock to the trap, all right? It's happening like this. So in the secondary migration, it happens by buoyancy forces, capillary pressure effects, and the hydrodynamics through the continuous water field forces. So it can take place over large distances, thousands of meters maybe. All right, we are talking about. Okay, well, this is important. Hydrocarbon traps, faults and falls form effective structures to trap hydrocarbons actually. Okay. And the oil and gas accumulate in the dome. The seal prevents them from escaping upwards. So the seal that we are calling in the upper part of the formation of the reservoir must be impermeable. Okay, there must not be any place that it can escape from there and go in upwards with the buoyancy. All right. So the type of the seals we classify as cap rock. Against 65% of them nearly are shales. Evaporites, which salts, we classify as 33%, and the carbonates 2%. All right. So measure source rock and the migration path required to make this efficiently to enable this actually. So that's what we can say. All right, that's what we can say. There are some domes as well, salt domes. We will mention about that. These are necessary to trap the hydrocarbons. A proper seal is required to keep the hydrocarbons in place. A barrier which is not 100% impermeable will not allow oil to stay in place over the course of a million years. Okay, so it has to be 100% impermeable. All right, to prevent any escape. Okay, any migration to the uppers. So shale is the most dominant cap rocks of the worldwide reserves. Evaporites, salts are the most efficient although, alright? And the dome above shows gravity separation of fluids. That's what I can see, the summation of this slide actually, okay? Okay, very good. So let's continue. A geometric configuration of the structures and or strata in which permeable rock types, the reservoir, are surrounded and confined by impermeable rock. Okay, impermeable rock types. So structural traps are the anticlines, faults, and salt diapers, salt domes are the example of this. Stratigraphic traps, salt diapers domes are also the part of that. Unconformities, some unconformities included in this category. Reefs and the others, we can classify some other complicated structures. There are some also combination traps which can be formed by including some structural and stratigraphic traps too. All right. Okay. So for the dome structure is oil and gas migrate upward from the source beds until trapped by the impermeable cap rock. We already mentioned about this. Right? So what about the salt dome? For the salt dome, okay, as you can see here, there is a structure for the salt is formed as can be seen in the figure. Okay, this is a generic shape. It can be okay, of course, it can be changed, but gas, oil, and water, respectively, get their places according to this, and salt also is impermeable. So as you can see, it's separating two different parts. So you can classify. Of course, they are in fact they are not one reservoir, but in this section we can classify it as two different reservoirs in here because it's impermeable and there's a trap in the above parts. So if there's a migration, so it's a different story. But if these are also impermeable, so we can say there's a trap. They trap in two different sections, and although they belong to the same structure and the same reservoir in once upon a time, now we can say they are different zones. All right. Okay, let's go. So trap formed by the fault also, as you can see the example, if there's a fault in here, there's a fault plane and there's a force causing the fault, of course, by time. Okay, by time it's causing. And if there's an impermeable bed in here, so the structure of the impermeable bed is changing. The elevation of the impermeable bed is changing sourced by the fault part, of course. So what's happening in there? For example, you will see the water, and there will be a connection between these waters, but because of the fault, the connection lost. All right, and the gas, oil, and water is formed in the as you can see in the right section in a different way, and the left section is totally different. All right, so trap can be formed by the fault. All right. So another one is the unconformity trap. So as you can see here, there are some impermeable beds which enables to form gas, oil, and water in this category, this section, relatively. All right, respectively, actually. Okay. So this kind of unconformity trap, because you cannot classify it, there's unconformity. As you can see, it can be in different shapes as well. So we classify this as unconformity. So the type of the structure, actually, what we can say, the rocks compromising reservoir undergo the significant change due to the tectonic movements. All right. So the most important is folding and the faulting. All right. As it is these alterations to the initial horizontal strata which creates the structures forming the reservoir traps. Okay. So the depositional environment contributes greatly to the variety of the trap. Shallow lagoons can have the reefs as well as the layers of the carbonates. All right. So the type of the structure depends on the stress regime and the rock type. So there's two different stress regime we can talk about. There's a brittle and the plastic deformation. Okay, brittle and the plastic deformation. Brittle deformation yields faults and the fractures. Plastic deformation yields faults and diapirs. Diapirs. Okay, sorry. Okay. So the stress regime governs the shape of the structures as well. Okay. Let's go. For example, faulting could be pads or barriers for oil. Okay, there's one example from the Anatolia here given. Canap Canyon in Utah. Another example, as you can see, because of the trap, the elevation of the structure is changed. For example, you can see some black part in here, maybe shales. Okay, and it moved to the upper part in here. Okay. So in Anatolia also example, you can see the same thing, how it formed and how it changed the location, okay, because of the fault. Okay, so small scale normal faults offset once continuous rock layers. Small scale faults like these are often parts of a larger fault zones. Okay, faults are important as they may act both as pathways for oil, for example, especially in shallow depths, or barriers at the great depths. All right. Okay. So another one is the example for the folding and the plastic deformation. An outcrop of originally horizontal rock layers bent into overturned faults by compressional tectonic forces. So smaller faults develop in the axis of faults actually. Okay. So we may also get faulting. The dark bands have flowed and they have thinned on the limbs of the fault and thickened it on the axis actually. Okay. So these are good examples for the plastic deformation. As you can see, it's not broken too much. Okay, in the big picture, it's not broken, but it shows some folding. Okay, some folding. Yes, all right. Okay, so by folding, what happened? It forms some structures called anticline and syncline. Okay, the young rocks in the upper part of the rock in the lower part. Okay, anticlines fold upward direction and synclines fold downward direction. Okay, upward direction anticlines, syncline in the downward direction. So it demonstrates the principle of the superposition. All the rocks we set beneath the younger on top. All right, always. Okay. So let's go for the type of the traps here. Anticlines, we said. The faults we already mentioned. There can be some salty appears in here. There are some unconformity traps. All right. Some reefs also can be here. Some reefs. Other stratigraphic traps, which are, as you can see, very heterogeneous. And there can be some combination traps of all of these. Okay, maybe 3, 4 of them at the same time. You can see in the literature. It's enabled. So anticline fault and salt appears we describe as structural. Salt appears unconformity reef and other stratigraphical we call stratigraphical traps. Okay, and this is the combination traps. Okay, okay, we already did this one. So what about the seal? Let's talk about the seal a little bit. So impermeable barriers. They are cap rocks. They are impermeable barriers. They are any type of seal that we can say impermeable. Permeability has to be very low and nothing. Okay, 0.0001 maybe, right? So think about that. Yeah, very low permeability. So the type of seals, again, we said 65% shale, 33% evaporized, and 2% of carbonates is formed. Okay. So the reservoir structure. Okay, there are many other types of structures. So the criteria for a structure is that it must have the closure. The fluids are unable to escape, as we said, and it has to be large enough to be economical. Okay, if I open a well and produce, if I open a well with 2,000 meter depth and produce 12 days and then it exhausted, it's not feasible, it's not economical. So after 12 days, you have to shut in the well. All right. So it's happening actually. It happened before lots of time in Anatolia section. Okay, why? Because because of the earthquakes that we already did, because of the earthquakes and other movements, the fault movements, the cracks happening a lot, and all the cap rocks are having some brittle deformation, and their impermeability, all right, is changing. Okay, they are not becoming impermeable because of the deformation. All right, cracks happening, some type of faults happening. All right, it's finding a way to go to the upward direction. So very little amount of reserve is staying in the place in the reservoir, and then when you open the well, you can produce up to 10 days, maybe 15 days, and then the pressure go down, right? And you're saying that it's not feasible, I have to close the valve, right? There's nothing to do with that, and I have to close the valve, right? So the exact form of the reservoir depends on the depositional environment and the post-depositional events, such as folding and faulting. That's what you can say. In the reservoir, there are two required basic fundamentals. One of them is the porosity, the void space, and the other one is the permeability, we said. And the most common reservoir rocks are sandstone 60% and the carbonates 39%, and the others 1% around, right? That's what we can say. So the keywords and the concepts that I would like to mention in here, first of all, rock cycle, rock types, plate tectonics, sedimentary rock information, clastics, non-clastics, porous or fractures also, formation, migration, trapping of hydrocarbons, and rock structures involved in the hydrocarbon trapping. Okay, so these are the main things that we have to mention when we are making our evaluation, right? So, okay, in this section we will mention about the porous permeability and saturation, wettability, and oil properties, some fluid flow through the rocks. Okay, we will explain how it's setting these parameters. We will explain the detail of the three reservoir drive mechanisms and explain enhanced oil recovery and explain the secondary recovery. What are these? What they meaning? All right. So we will try to explain all of these in this explanation part. These are very crucial for the offshore environment as well, right? So for first of all, a basic reminder to all of you, all right? So porosity, okay? So porosity, we said the pore space between your rock particles, okay? So represented by the P, all right? And range from 5 to 30% for most of the reservoirs. And for the primary one, it's formed during the deposition. I am talking about conventional reservoirs in here. Don't forget it, conventional reservoirs. It ranges from 5% to 30%. The primary one formed during the deposition. The secondary one formed after the deposition. Okay. So there can be some packing differentiations in terms of the dimensions. All right. For example, rhombohedrali packed spheres, it's around, if the shape is around this one, so we can say it's 26% around, right? If there is a kind of shaping like this, the grain sorting, silt, clay, and cementation of effective porosity, here as you can see, there are some type of porosities as well. So we will mention all of these about, all right? Uh, if, for example, there are some more different types of that. There are some more different types of that. I will definitely mention with this one, all right? The effective porosities as well. So let's go to this, all right? Let's go to this. Ah, porosity, rock matrix and the pore space. Here is the pore space, and the rock matrix is described as a very heterogeneous part of that, and the pore throat, as you can see, very low in here, which affects in this part, for this part, the permeability, right? The open space within the rock is the pore space. We call it porosity, and it's always measured in persons, all right? It's measured in persons. So packing of the spheres. So cubic packing for the porosity gives you the 48% porosity, all right? 48% in total. Rhomboid packing, it gives you 26, we said 26, 27% around, all right? And if there's a two sphere size, all right? So in this case, we said porosity is around 14%, okay? Around 14%, right? So let's go. Three main types of porosities in here. One of them is interconnected, multiple pore passages between the grains, fractured, only one pore passage, we call cracks, right? And isolated, no connection between the pores, okay? 1 plus 2 we call, if there's a calculation called which includes the first one, the interconnected, and the fractured one, we call it the effective porosity, okay? So the ratio of the effective porosity to total porosity is very important in here. So why? Because it describes our permeability. Okay, it gives an idea regarding our permeability. All right. So the porosity is not affected by the grain size. Porosity is affected by the grain sorting. Okay. Let me clean this one. Okay. Porosity is affected by the grain sorting and the angularity. Okay. So rhombohedral or square. All right. As we can see here, cubic packing or rhombohedral, all right? What type of packing is that? According to that, it affected, all right? Okay, so let's go. So example of the porosity types. Let me clean this one again. So this red one, okay. We can see it clearer now. So example of the porosity types, interconnected porosity, as you can see, the pore spaces are connected between each others, all right? the fracture porosity. The main dominating mechanism is the fractures in here, as you can see. All right. And the isolated porosity, okay, there is no connection between the pores. In some parts maybe it can be, but some parts if there is no connection and the fluid is actually trapped between the pores, we call it isolated porosity. Okay, so three main types of the porosity we are talking here. Okay, the primary porosity, intergranular or intragranular. So if it is intergranular, so you can see much more homogeneous compared with the intragranular one. So for the intragranular one, it's a little bit more complicated and the heterogeneous structure you can see here. So in the intragranular one, you have to count the isolated porosity part as well. All right. Okay. So for the secondary porosity, so you can see different shapes in here. All right. You can see different shapes in here. Okay, let me open this pen. Okay, so here, as you can see, the fenestral shrinkage type of the porosity, intercrystallines. There are some crystalline materials, rocks in here, and there are some intercrystallization in between the crystals happening. All right, geologically, if we want to describe. So if you see this type of structures, so we can say this is a part of the secondary porosity. So the second one, the solution, leaching of solution, mold and vuggies, some wax and some moldic structures can be seen in here. If you see these tips, so you can say this type of structures, you can see secondary porosity. Another one is the fracture, is the secondary porosity directly. If you see some structures, carbonate structures can be mostly in limestones as well. So if you see these structures, then you will say there's a fracture, right? There's a fracture. You can say there is a porosity, secondary porosity in here as well, all right? Okay, so porosity tests. What are these porosity tests? One of them is the E-logs, gives the total porosity values. Sonic logs, neutron logs, density logs giving this one. And the second one is the core test, give effective porosity values. If you take some in situ samples from the downhole, get these samples to your laboratory, and you can measure your water saturation, gas saturation, and the mercury injection. Okay, and it gives you the porosity as effective porosity, right? And for the logs, it gives you the total porosity one, right? Don't forget this. Okay, let's go. The permeability, while the porosity is the measure of the fluid contained with the rock, the pore space must be interconnected for the fluid flow. So matrix permeability in oil reservoirs around 100 millidarcy to 3 darcies. Fracture permeability is 5 to 15 darcies, alright? So Henry Darcy investigated the flow of fluids through the porous media in 1856 to solve the problem of sewage problem of city in France, right? And devised a measure that carries his name and is represented by a small constant, alright? So the permeability can be described with the formula that Henry Darcy is given, alright? So permeability is dependent upon the arrangement of the grains and the type of the cementation process that has occurred, actually. The permeability is the basics of how fluids flow to the wellbore and one of the most important factors of any type of commercial production of the hydrocarbons to occur, actually, right? So the petroleum industry adopted the Darcy as a unit of the permeability. So it's defined as a porous medium has a permeability of 1 Darcy when a single phase fluid of 1 centipoise viscosity that, let me open this, okay, a porous medium has a permeability of 1 Darcy, I am repeating, when a single phase fluid of 1 centipoise viscosity that completely fills the voids of the medium will flow through it under the conditions of viscous flow at the rate of 1 cubic centimeter per second, okay, per square centimeter cross-sectional area under a pressure or equivalent hydraulic gradient of 1 atmosphere per square centimeter. Okay, it's a description. All right. Okay, then let's go to the next slide. Effect of the grain size on permeability. As you can see, if we are talking about the large grain size, it resulted with the higher permeability with the large grain size. Okay, So the porous, the area, the volume for the porous is increasing as well a little bit, but better than that, we can say higher grains result with a higher speed, all right? And so it's reaching to a total. You can consider the total speed actually, all right? Like valve, right? By the time it will become bigger and bigger. So if we are talking about small grains, it will result. So each velocity will be considered indifferently, all right? And then we will talk about the transmission from one port to another will be harder compared to this one. Because of the effect of this transmission, the velocity is decreasing. And for the small grains, we can say it resulted with the lower permeability, all right? Okay. So oil-water contact, I will talk in here in this transition zone. It's longer for the low permeability cases actually. Let me open this. Sorry, let me open this. Okay. So let's say water irreducible water saturation in here and the oil zone in here. 100% oil production you can reach in here if your well end part of your well is somewhere here and your perforation is somewhere here, 100% oil you will produce. But if your well comes cross through this section, oil water transition zone, you will produce some water, of course. Okay, if you go below this level and go through to the water zone, then it's unlucky. So you have to close that part of your well and go up and perforate again. All right. So there are some permeability tests we call MDT, RFT, and well testing and core sampling, which allows us to describe have an idea regarding on also the oil-water contacts as well. All right. That's what we can say. And then the ability to flow through the rock. Okay, saturation, wettability, and oil properties are affecting this as well. Right. This is very important. And for the saturation, let's talk about the saturation, amount of water per unit volume. Okay, porosity times water saturation. Amount of the hydrocarbon per unit volume, porosity times 1 minus water saturation. Okay, so the porosity, oils included, oil saturation and water saturation both inside, right? And the rock volume is in here as well, and the total volume is included, all right? Okay, so the percent of the pore volume occupied by the particular fluid, water, oil, and gas. It can be water saturation, oil saturation, gas saturation. This is the main description. And range or typical values, let's say 15% to 25%. The connate water saturation is well sorted coarse for the well sorted coarse sandstones, and 40 to 60% for the connate water saturation in the poorly sorted, fine grained, shaly, low permeability reservoir rocks. Okay. That's what we can say. So how we get this one? The symbol is where we call SW, SO, and SG. Okay, and the units are mainly our fractions or percent, maybe you can say. Okay, the source of taking this mainly from the logs. Okay, from the well logs. Mainly we are taking this. Some core also from the cores we can take, but the fastest one that we get these values are from the logs. Okay. Okay, saturation and the grain size. Small grain size gives you higher irreducible water saturation, and the larger grain size gives you lower irreducible water saturation. Okay, so physically we have to think about that. Okay, this is a potentially good question for the first week in the exam. It can be a good question. So what is the reason of this one? All right. So why small grain sizes gives you higher irreducible water saturation, and the large grain size lower one. All right. So you have to think about that in the physical section. If you make it lower and lower, the pore sizes, okay, grain sizes actually. So your the connection between the rock surfaces will be closer, and the pore troughs will be closer, and the dominated mechanism in this case will be what will be the capillary pressures. So capillary pressure and the wettability will affect what your saturation deficit, irreducible water saturation, because if your capillarity is becomes higher, all right, it will be harder and harder to get that part of fluid from that pore throat as well, pore place as well, right? So this is the reason. So the result is the wettability. If I ask this one in the exam, I will ask you, please go and search with this topic. I will ask for the details definitely, right? Okay. If you have any questions, you can directly ask me as well, right? You can reach me. Okay, so the wettability. Wettability is the addition of a liquid to the surface of a solid. The sedimentary rocks are water wet before contact with oil. Some solids are rather in contact with the water phase, okay, the water wet, and then with an oil or gas phase called oil wet, okay. We describe the wettability actually as the tendency of a fluid to spread on a surface while that fluid and other immiscible fluid also in contact with that surface, okay. So there are two fluids which are immiscible. They are not miscible, okay. They are immiscible fluids, and they are in contact with the rock surface, okay. So it's a tendency of the surface, rock surface, to choose one of them to spread in its phase, okay, in its surface phase, all right. So we can describe this one. So in water wet conditions, a small film or water coat on the surface of the formation matrix, which is desirable for the efficient oil transport, okay. So if it's water wet, it means that your rock likes water and tries to keep the water much more than the oil. So that's what I want actually. If the rock is water wet, this is definitely something that I like, all right, because I can get the oil easily compared to the water one, all right, compared to water phase. Okay, that's very important. That's very important actually. Okay, all right. So the contact angle as a measure of wetting, as you can see, if it shows a complete wetting with zero contact angle, the presence of the gas and liquid in here spread on the surface is completely showing zero contact angle and completely wetting the surface. Okay, the liquid one. So partial wetting, contact angle is around 30 degree. All right. So for the liquid and gas in the second phase. Okay. So for example, the first one, air and water, shows kind of behavior like this. And the second one is isooctane with water, showing a behavior like this. Okay. Still is water wet. All right. And when it comes to isoquinoline, all right, isoquinoline, kind of chemical compound in the gas phase, okay, and the interaction between this one, between the water with the rock surface, so it shows a kind of low degree of wetting, and the contact angle is around, you know, more than 180 maybe here. I will check it. Yes, this is 153. Okay, it shows according to this. Okay, 153. So this is definitely the rock surface doesn't like the water. We can say it is here isoquinoline wet. Isoquinoline wet. Okay. So if you put, in some cases, if you put the oil in here, okay, oil and water in the liquid phase, both of them, right? So you can see some type of behavior like this between the oil and water as well, according to the type of your rock, right? Okay, I think we classified this well, and then I'm continuing with this one. So the implications of the wettability. Wettability affects the shape of relative permeability curves. Oil moves easier in water wet rocks than the oil wet rocks. The primary oil recovery is affected by the wettability of the system. A water wet system will exhibit greater primary oil recovery. Oil recovery under water flooding is affected by the wettability of the system. Okay, and water wet system will exhibit greater oil recovery under the water flooding. That's what we can say. So in the production, okay, especially for both, that we can say for the onshore and offshore. So we have to find the way to compare the volumes, okay, between the surface and downhole. So we have to always get into account that the downhole conditions and the downhole volumes of your oil, water, and gas is not same when they come to the surface. Okay. There is a BO, we call BO, formation volume factor of oil, and the volume of your oil will be compared to that will be lower when it comes to surface, because some part of the gas which is soluble in downhole in that condition, in that pressure and temperature, will be what will be apart from the oil volume, right? And we could RS the solution GOR. It will be some, the gas will be aparted, because when it comes to surface, your pressure and temperature is going lower. When it goes slow, the gas phases go like the cola. When you open the cola, okay, cola can, what happens? The pressure is down, and some part of gas go from the solution phase, it goes through to the gas phase, right? So the same thing happening when it comes to coming to the surface, okay? So for the gas, there's a free gas in here. When it comes through to the surface, and we call BG, formation volume of gas comes here, and the free gas volume comes, and some solution gas comes from the oil, and some solution gas form comes from the water phase as well. So water is not same as well. So formation volume factor of the water also happens. Some water phase pass to gas phase, and in the total gas phase calculation from the reservoir through to the surface, when we said in the surface we have to add the solution gas and the solution gas of oil, solution gas of the water as well, right? It's very crucial. And the volumes will be totally different. So you have to calculate your GR values are very important. RS values and the BO, BG, and BW values are very crucial to be calculated to make the correct calculations. This is the main fundamental thing of the production. All right, oil and gas production. All right. Good. Let's go on. Okay, for the reservoir drying mechanisms I will talk. Hydrocarbons will flow if the reservoir pressure is sufficient to drive the fluids to the surface. Otherwise, they need some form of artificial lifting. As the fluid is produced, the reservoir pressure drops according to the reservoir drive mechanisms. So drive mechanisms depends on the rate at which fluid expands or replaces the produced fluid. Right? Three main drive mechanisms we have. Okay, now it's time to discuss the primary drive mechanisms that occur during the production. It should be noted that some type of the expansion or replacement must take in place in the reservoir before any fluids can flow to the wellbore. Okay. So possible sources of the replacement for the produced fluids are the expansion of the undersaturated oil above the bubble point we are talking about, the expansion of rock and of the condensate water, the expansion of the gas released from the solution in oil below the bubble point, the emission of the original oil-bearing reservoir by the expansion of the gas forming the free gas cap, the emission of the original oil-bearing reservoir by the expansion of the water form an adjacent or underlying aquifer. Okay, and these expansion mechanisms are not usually considered separately, and the three principal categories we can say as below the bubble point, the expansion of the fluids are negligible, and the drive is achieved by the release of gas coming out of solution. So when the gas saturation get high enough, the free gas will begin to flow, and the GR may become excessive. Okay, this is the thing. So three main drive mechanisms we say: solution gas drive, gas cap expansion drive, and the water drive. All right. Okay. So for the solution gas drive, the depletion drive mechanism, we can say, as you can see here, oil producing wells here, and the oil you are in the oil part, oil zone, right? The original conditions, there's an aquifer formation in here, and what's going oil start to be produced. When oil produced, by time it goes to 50% depletion, and what happens? The pressure is decreased. When pressure decreased, there are some bubbles of gas bubbles start to be formed. Okay, what happened? Because from the solution phase it passed to the gas phase. Okay, so by the time you start to produce much more gas as a result of this, right? So because of your lower pressure in your reservoir, less gas will be formed. More gas will be formed. Less solution, the more gas will be formed. So oil is produced by the expansion of the reservoir fluids and the gas dissolved in the liquid phase. Your reservoir pressure will be above, will be more than your bubble point pressure. Okay, so no initial gas cap and then no water influx in this scenario, right? So this is one thing If your reservoir pressure go down, all right, then your bubbles start to be show up, right? Okay. So solution gas drive, another one. An initial high oil production is followed by a rapid decline. Okay, typical behavior. The gas-oil ratio has a peak corresponding to the higher permeability to gas, right? And then reservoir pressure exhibits fast decline. It shows. Okay, the GR value. If you see when you are in the production of oil, okay, if you see your GR value is rapidly decreasing and showing a rapidly increasing and showing a decrease, okay, as a changing slope with a changing slope, all right. And your reservoir pressure is, as you can see here, showing a decrease in a certain manner, a certain behavior, and you can say this is a solution gas drive mechanism, all right, from the measurements of the pressure and your production rates. You can see this one, your GR values. You can see this one. Gas cap expansion drive. Okay, here there is a gas cap in the above part, all right, oil producing well, and the gas cap in the above part. So what's happening? This gas cap is forming, is giving you an additional pressure resistance, okay, from the upper part, and make it easier to produce actually. Okay, so this is something what I want actually, and I want to preserve this gas cap in there. Okay, I don't want to produce this gas cap. I want to preserve that gas cap in there to maintain the pressure assistance, which assists the oil phase, which allows me to produce. All right. So this is very crucial. It's a gas cap expansion drive mechanism. It's below the bubble point. You are below the bubble point. Expansion of the fluids are CW and CP negligible. We are not considering this. The drive is achieved by the expansion of the gas cap and the release of gas coming out of the solution, and no water influx in this scenario. If there's a water influx, then it's another scenario we can talk about. So gas cap expansion drive, okay? By time it will expand to maintain the same pressure assistance, okay? When you're producing, right? Okay, gas displacement. Gas is more mobile than oil, less viscous, and it takes a path of least assistance along the center of the larger channels, definitely. As a result, oil, higher viscosity, is left behind in the smaller, less permeable channels, and the reservoir pressure drops. Okay, so the very high mobility of gas for low viscosity means that it goes down the large pore channels by passing the small ones. Okay, passing the smaller ones. So once past the zone, the gas will continue leaving the oil, higher viscosity trapped, right? So it will not be produced. Okay, so this is important part as well. Okay, in the gas cap drive, the typical behavior for the reservoir pressure and oil production here, as you can see, by time there's a kind of decrease with oil production, and then for the reservoir pressure there's a decrease in a certain manner, and for the gas production it shows a kind of increase, which has a kind of asymmetry, okay, a kind of reverse symmetry, okay, compared with oil production, okay. So as oil production declines, gas production increase. The rapid pressure drop at the start of production can be seen in this, and this is the basic mechanism, typical behavior with the measurements of the pressure and oil production, all right, and gas production. We can get. So another one is the water drive. Instead of gas, then in this scenario, I have the water in the below part. Also, this is a good thing. It gives a pressure assistance. But the first thing you have to maintain that the water you are keeping in your reservoir directly, because by time it can show it can give a kind of conical behavior, and you can start to produce your water. And the percent of your water cut will increase by time. So what you need to do, for example, if you have a 500 well in a field, all right, 500 wells, so you have to describe what type, which parts showing the conical behavior, and you will make some cut on the production and lower your production in that parts, and which parts showing less, you will open that parts for the production, oil production, and you have to balance it, and you have to this gives you a kind of opportunity to manage your water phase, okay, your aquifer zone, without making any conical behavior and increase the water production. The first thing that I need to keep in mind, I want water stay in the reservoir. Why? Because I need pressure resistance all the time, as much as I can do. Okay, as long as I can do, I have to maintain this pressure resistance. Okay, never forget this. All right. So the oil being produced is replaced by water, keeping the pressure constant if the replacement ratio is close to 1 to 1. All right. It's the main thing that I would like to mention. All right. So because of that, you have to always ensure your reservoir management by making your models or getting your results of pressure, temperature, and rates, okay, for each phase. Water cuts, water cut values, these are very crucial. By this one, you have to manage your reservoir well to maintain your pressure, reservoir pressure for a longer time, right? So this is the water dry mechanism that I would like to mention. And the water displacement, another one is water displacement. The remaining trail of oil becomes smaller. It finally breaks into smaller pieces, and as a result, some drops of oil are left behind in the channel. So there will always be some oil left in the rock. 100% recovery is impossible. Okay, so the residual oil fraction, SOR we call, is important as it controls the amount of the recoverable oil. Okay, there are some methods. There are some methods to decrease this residual oil fraction. All right. Especially some chemical methods is applied. So this is very crucial for getting the most efficient production from your reservoir. Okay, so for water drum replacement mechanism, so this type of drive usually keeps the reservoir pressure constant, we said. After the initial dry oil production, water may be produced. The amount of the produced water increases as the volume of oil in the reservoir decreases. Dissolved gas in the oil is released to form produced gas. Gas oil ratio we call GOR will be almost constant over time since the reservoir pressure is much more above than your bubble point pressure. Okay, so the production of water will invariably increase. The amount of the water finally produced depends on the capabilities of the surface production facilities and the economics of the process as well. Very crucial, all right? So it can be as much as nearly 98%, okay, we say. Gas production is simply that associated with the oil and depends on the gas oil ratio too much, okay? Too much dependent, all right? Okay, for the replacement mechanisms, that's the things that we can say. And the main behavior, typical behavior for the water drive, as you can see here, for the reservoir pressure and oil production, the gas production. So gas production shows a little decrease, not too much decrease or increase, but it shows a very slight fluctuation. Your oil production is lowering by the time they decrease, but your water production is increasing by time. So you have to manage it well to decrease to slower this increase. It will increase in that, no way out, but you have to slow this. Instead of 3 years, maybe you can see it in 5 years. Okay, so the behavior. Okay, so you have to your aim in this type of mechanism. You have to keep it in constant value, or you cannot keep it in constant value, but you need to decrease this slope actually. Okay, decrease this slope as much as you can do, right? In the lifetime of your well, actually. So, okay, then there's a water dry mechanism, as you can see by time. Q oil in here, and the weight of your oil by time is increasing and then decreasing, start to decrease. Your water is start to increase. Because of that, your oil weight start to decrease, and your GR value is going decreasing slightly, so your gas phase doesn't have any problem about that. But and also your pressure value, okay, pressure value shows some decrease. Because why? Because you are losing your pressure resistance by time, which is sourced by your total production, of course, but mostly from your water production. You are producing water, you start to produce water more, and then you start to it's showing that your reservoir pressure is going lower by time. Okay, so because of that, it's going to it's certain thing that you are going through to the abandonment. So you have to you have to develop a kind of solution for this one. Maybe you will use some ICV inflow control valves to control your the volume that's coming to your wellbore, the volume of your water coming to the wellbore from the side. That's the water coming. All right, you can describe it by measurements, logs especially. So before abandonment, you have to make it longer. The life of your reservoir actually. Okay, the well actually your well, right? So drives, recovery drives, so solution gas drive, gas cap drive, and for the water drive, initial reservoir pressure with the oil recovered, we can say for the water drive, it's giving you the highest actually performance, and the solution gas drive and the gas cap drive, the percentage of oil recovered is lower compared with the water drive. So I have to maintain my water keep inside the reservoir. This is the first thing. If I make it in a correct way, then the life of your reservoir will be longer and longer. Okay. For the solution gas drive, it's the less it's very low compared to the gas cap drive and the water drive. And the gas cap drive also gives you some kind of pressure resistance, not like water drive, but it gives you a kind of pressure resistance, unless you keep it in one phase, okay, gas phase, and you keep it in one phase. If your reservoir pressure is above your bubble point pressure, then it will be a kind of good solution for the gas cap drive as well. All right. Okay, so let's go. Combination drive reservoir. Another thing, this actually in real world we are seeing this too much. What's going? There's an aquifer in the below part and there's a gas cap in the above part, right? So the oil zone becomes in the middle, and then actual reservoirs usually present more than one drive mechanism acting at the same time. That's what I said. Okay, so then you have to describe the scenario, what type of reservoir you have, and you have to maintain the as much as longer its life. All right. So you have to get the precautions in a correct way that you can do. All right. Okay, that's what you can say. So for the dry problems, what's happening? For the water dry, water can cone upwards and then be produced through the lower perforations. It's very important. Gas cap dry, gas can cone downwards and be produced through the upper perforations. Pressure is rapidly lost as the gas expands. Okay. For the gas solution dry, gas production can occur in the reservoir and skin damage can be happen and very short-lived. You have to be very careful with these things. These are the production problems sourced by the completion mechanisms. Okay, so we have to be very careful with these type of things. And the coning, as I mentioned, coning is caused by producing the reservoir at a drawdown that's too high and also having perforations that are too long. Okay, for long perforations, you have to describe. You have to be very careful when you are giving the length of your perforations in the beginning. All right. So the water or gas is drawn to the perforated interval and produced. Okay, so we don't want these type of things for a long-lived well, right? So secondary recovery covers a range of techniques used to augment the natural drive of the reservoir or boost production at a larger stage in its life. A field often needs EOR techniques to maximize its production. Common recovery methods are water injection and gas injection, or water alternating gas, WAG we call. In the reservoirs containing heavy oil and other recovery methods are used to reduce the viscosity. Steam flooding, SHGT, steam assisted gravity drainage, is a part of that. I have some papers with these ones I will share with you, all right? I will give you the address via WhatsApp or another sources, all right? And the polymer injection is a part of that. Carbon dioxide in the injection is another thing. These are the secondary recovery methods that we can mention. Here, as you can see, that there is a water injection from the water zone, from the aquifer, mainly it's injected, all right, to maintain the pressure assistance of the aquifer is main thing. For example, if you are producing some water, so you can separate the water in here and re-inject it to the reservoir. It's a kind of solution. Another one is the gas injection one. So what's going on? Oil production, separated oil and gas separated. Gas is re-injected to the reservoir to maintain the pressure of gas and to prevent your reservoir pressure go below your bubble point pressure. All right. So these are the precautions that can be done as a secondary recovery. It's a very important part of your production, the life of your reservoir, and the effective production actually. Okay, These are applied in both onshore and offshore as well. So for the next weeks, we will concentrate on the offshore. After these basic informations, we will concentrate on offshore environments, how we are doing this, how we are making this type of stimulations, all right, in our wells, and what are the parameters that we have to take care about that. We will discuss all of these, okay, in the next upcoming weeks. So this is the end of the second week course. I hope that you enjoyed listening this one. I will share the slides as well with you. I will give you the link, all right, for the each week slides, right, PDFs. And I hope that you enjoyed the course. See you in the third week, all right? Take care of yourself.